Distributed Systems from Scratch. This is episode 13, Distributed Storage. The opening of season 3, Building Real Systems. In the next 10 minutes, you'll understand the storage engine inside almost every modern database and the 3 Google papers that quietly defined how the entire industry stores data. Season 1 gave us the theory, CIP, consistency models, impossibility results. Season 2 gave us the protocols, consensus, replication, partitioning, gossip. Season 3 is where we put them all together. We're going to study real systems, systems that store petabytes, process millions of events per second, and serve billions of users. And we're going to understand how they are built from the protocols we already know. We start with storage because everything sits on top of storage. How do you store petabytes of data reliably? A single disk holds maybe 16 terabytes. A single machine with many disks maybe 100 terabytes. But Google, Facebook, Amazon, they deal in exabytes. That's millions of terabytes. You need storage that spans thousands of machines, that never loses data even when machines die, that serves reads and writes at enormous throughput. Two foundational questions make this possible. First, the storage engine. How do you organize data on a single machine's disk for efficient reads and writes? This is the local data structure problem. Second, the distributed file system. How do you spread files across thousands of machines and keep them safe? This is the coordination problem. Let's tackle the storage engine first. Storage engine number 1, Bitrees, the workhorse of databases since 1970. Nearly every relational database uses Bitrees. PostgreSQL, MySQL, SQLite, Oracle, all Bitrees under the hood. A B-tree is a self-balancing sorted tree structure. Data is stored in fixed size pages, typically 4 to 16 kilobytes. The tree has a root page, internal pages that act as signposts, and leaf pages that hold the actual data. To find a key, you start at the root, follow the pointers based on comparisons, and arrive at the right leaf in O of login. Page reads, very fast for point reads. Writes update pages in place. You find the right leaf page, modify it, and write it back. If the page is full, it splits. Since writes modify existing pages, you need a write ahead log for crash safety. Write the change to the log first, then apply it to the tree. Bitrees excel at reads. One traversal gives you the answer. Range scans are efficient because adjacent keys are on adjacent pages, but writes involve random I/O. You're updating a page somewhere in the middle of the disk. On spinning disks, random I/O is slow. On SSDs, it's better, but still has write amplification costs. Storage engine number 2, LSM trees, log structured merge trees, optimized for writes, the engine behind most modern distributed databases. An LSM tree takes a fundamentally different approach. Instead of updating data in place, all writes go to a memtable, an in memory sorted data structure, typically a red black tree or skip list. Simultaneously, every write is appended to a write ahead log on disk for durability. If the machine crashes, the memtable is rebuilt from the WAL. When the memtable fills up, typically a few megabytes, it's flushed to disk as an SS table, a sorted string table. An SS table is an immutable sorted file of key value pairs. Once written, it never changes. Over time, many SS tables accumulate. They are organized into levels. Level 0 has the freshest data. Level 1 is larger. Level 2 is larger still. A background process called compaction periodically merges SS tables from one level into the next, removing duplicate keys and deleted entries. Reads check the mem table first, then SS tables from newest to oldest. Bloom filters help skip SS tables that definitely don't contain the target key, avoiding unnecessary disk reads. The key inside writes are always sequential. You append to the WAL, then flush sorted data to disk. No random I/O, This makes LSM trees dramatically faster for write-heavy workloads, 10 to 100 times faster than B trees for pure writes. Let me compare them directly. Write pattern. B trees use random I/O, update it in place. LSM trees use sequential I/O, append only. Sequential I/O is much faster, especially on spinning disks. Write throughput. LSM trees win by a large margin, 10 to 100 times faster for write-heavy workloads. Read latency. B trees win one tree traversal versus checking multiple SS table levels. LSM reads might touch several files before finding the answer. Space usage. LSM trees are more compact because compaction removes duplicates and reclaims space. B trees have more fragmentation due to page splits, write amplification. Both have it, but in different forms. B trees rewrite the page plus the WAL entry. LSM trees rewrite data during compaction. The same data might be compacted through multiple levels. PostgreSQL, MySQL, and SQLite use B trees. Cassandra, RocksDB, LevelDB, and HBase use LSM trees. Now, let's zoom out from single node storage engines to distributed storage. And there's no better place to start than the paper that defined it. Google File System, GFS, published in 2003, one of the most influential systems papers ever written. GFS was designed with unusual assumptions that turned out to be prescient. Hardware fails constantly. GFS was built on commodity machines, cheap, unreliable hardware. Failure was expected, not exceptional. Sound familiar? That's the same mindset from our fault tolerance episode. Files are huge. Multi-gigabyte files were the norm at Google. GFS optimized for large sequential reads and writes, not small random access. Appends dominate. Most writes add data to the end of a file. Random overwrites are rare. This shaped the entire architecture. Throughput over latency. Google's workloads were batch oriented. MapReduce jobs processing terabytes of data. High throughput mattered more than low latency for individual requests. The GFS architecture has three components. The GFS master stores all metadata, the file namespace, the mapping from files to chunks, and the location of each chunk's replicas. The master is a single machine. This is a deliberate design choice, not an oversight. Keeping metadata in memory on one machine makes it fast and simple. Chunk servers are the workhorses. Each one stores actual data. Files are split into 64 megabyte chunks, and each chunk is replicated on three different chunk servers by default. The client talks to the master to learn where chunks are located, then reads and writes data directly to the chunk servers. Data never flows through the master. This is critical. If the master handled data, it would be an immediate bottleneck. By separating metadata from data, GFS can handle enormous data throughput. The master detects chunk server failures via heartbeats. When a server dies, the master notices the lost replicas and initiates re-replication from the surviving copies. Self-healing storage. Two key ideas from GFS. First, separate metadata from data. The master handles only the namespace and chunk locations. Actual bytes flow directly between clients and chunk servers. This eliminates the master as a data bottleneck while keeping the architecture simple. Second, chunk replication. Each 64 megabyte chunk exists on three servers. When a server dies, the master detects it via missed heartbeats and re-replicates the affected chunks from the remaining copies. The system heals itself without human intervention. For those familiar with Hadoop, HDFS is an open source implementation of the GFS architecture. The HDFS name node is GFS's master. Data nodes are chunk servers. The design is essentially identical. If GFS is the file system, Bigtable is the database built on top of it. Published in 2006, the second paper in what we might call the Google trilogy. Bigtable's data model is a sparse, distributed, sorted map. Every piece of data is addressed by three keys: a row key, a column specified by family and qualifier, and a timestamp. The row key is the primary index. Rows are stored sorted by row key. Notice in the example URLs are reversed. com.google instead of google.com. This puts all pages from the same domain adjacent to each other on disk, giving locality for scans. Column families group related columns. All columns in a family are stored together on disk. This is a physical storage decision, not just logical. It means reading one column family doesn't require touching others. And every cell can store multiple versions, each with a timestamp. You can read, give me the version of this page from last Tuesday. Old versions are garbage collected based on configurable policies. The resulting address is a three-dimensional key, row, column, timestamp, maps to a value. Simple but powerful enough to model most workloads. What's beautiful about Bigtable is that it doesn't invent new infrastructure. Look at the stack. Bigtable sits on top, and underneath it, three systems we already know. The storage pillar is GFS, SS tables, and write ahead logs live on GFS. So replication comes for free. Bigtable never touches a disk directly. The engine pillar is the LSM tree from earlier in this episode. Each tablet server runs one locally. Memtable in memory, SS tables flushed down to GFS, compaction in the background. And the coordination pillar is Chubby, Google's distributed log service built on Paxos from episode 6, master election, tablet server discovery, schema storage. Chubby is Paxos in production. That's the design lesson right there in the picture. You don't solve every problem from scratch. You compose well defined building blocks, a file system, a consensus service, a storage engine into something greater than the sum of its parts. The Google trilogy, GFS, MapReduce, and Bigtable spawned an entire industry. GFS became HDFS. Then cloud object stores like S3, Google Cloud Storage, and Azure Blob Storage absorbed most of its use cases. MapReduce became Hadoop MapReduce. Then Spark and Flink largely replaced it with more flexible processing models. We'll cover Flink next episode. Bigtable became HBase, a direct clone, then Cassandra, which borrowed the data model but replaced Bigtable's single master architecture with a peer to peer gossip ring. DynamoDB borrowed ideas from both Bigtable and Amazon's Dynamo Paper, and Google themselves offer Cloud Bigtable as a managed service. Three papers published between 2003 and 2006. They defined the architecture of nearly every distributed data system built in the last 20 years. The LSM tree specifically has become the dominant storage engine for distributed databases. LevelDB, Google's reference implementation of an LSM tree engine, single node only, used inside Chrome for indexed DB. RockSDB, Facebook's fork of LevelDB, faster, more configurable, production hardened. It's become the default embedded storage engine. CockroachDB, TyKV, and Kafka Streams all use RocksDB under the hood. Cassandra runs an LSM engine on every node. ScyllaDB rewrote Cassandra's engine in C++ for performance, keeping the same LSM architecture. When you hear distributed database, odds are there's an LSM tree inside. The distributed storage landscape today has four categories: block storage, AWS, EBS, CPHRBD, gives your virtual machine a disk that's actually backed by distributed storage, looks like a local drive. Object storage, S3, Google Cloud Storage, MinIO, a flat key to blob namespace, no directories, no locking, optimized for write once, read many, scales to exabytes, distributed file systems, HDFS, CPHFS, GlusterFS, POSIX, like interface across machines, good for analytics pipelines. Distributed databases, CockroachDB, Spanner, TIDB, full SQL query, capability over partitioned and replicated storage engines. the highest abstraction level. Each category serves different access patterns. Choose based on your workload. Let me connect this episode to everything we've covered. GFS's chunk replication is single leader replication from episode 8, with chunk servers as followers. Bigtable's tablets are range partitioned, the same range partitioning we covered in episode 9, with automatic splitting when tablets grow too large. Chubby is Pexos from episode 6, packaged as a log service for leader election and coordination. CockroachDB combines Raft from episode 7 for per range replication, LSM storage from today's episode, and both range and hash partitioning from episode 9. And Cassandra combines Gossip from episode 12, consistent hashing from episode 9, LSM storage, and leaderless quorum replication from episode 8. These aren't separate systems built from scratch. They are compositions of the same protocols we've been studying all along. Let's recap. 1. B trees optimize for reads with in place updates. LSM trees optimize for writes with sequential appends. Most distributed databases choose LSM. 2. GFS separated metadata from data, split files into replicated 64 megabyte chunks, and let clients talk directly to chunk servers. HDFS cloned this architecture. 3. Bigtable didn't invent new primitives. It composed GFS for storage, Chubby for coordination, and LSM trees for the engine. The lesson: compose, don't reinvent. 4. The Google Trilogy GFS. MapReduce, Bigtable spawned HDFS, Spark, HBase, Cassandra, and effectively the entire big data ecosystem. 5. Modern systems like CockroachDB and Cassandra are direct compositions of the protocols from seasons 1 and 2. Everything connects. Next episode: stream processing. How do you process an infinite stream of events in real time? Kafka as the distributed log, Flink for stream computation, watermarks for handling late data, and the Holy Grail, exactly once processing semantics from storage to motion. That's episode 13. Distributed storage, from B-trees to GFS to Bigtable to the modern landscape. The foundation everything else is built on. Next time, stream processing. Thanks for watching.